So let me now introduce our next speaker, Carlo Rubbia. Of course, it's impossible to do justice to his extraordinary career in a few minutes, but let me just start by saying a few things that you might not know about him. Carlo Rubbia is a Knight of the Order of Merit of the Italian Republic. There is a main belt asteroid discovered in December 1993 that is named according to him, number 8398 Rubbia. On the 30th of August 2013, Carlo Rubbia was appointed to the Senate of Italy as a senator for life by President Giorgio Napolitano. Of course, you all know that Carlo Rubbia was awarded the Nobel Prize in Physics in 1984 with Simon van der Meer for work leading to the discovery of the W and Z particles at CERN. What you may not know as well is that Carlo Rubbia was in fact the chair of the first LHC workshop that took place in Lausanne in 1984, which defined the parameters of the accelerator and the scientific program, with already at that time, of course, the Higgs search as the main item. As Director General of CERN from 1989 to 1993, Carlo Rubbia played a crucial role in bringing credibility of the LHC project at the time when the United States were building the SSC. Since the end of his mandate as Director General, Carlo Rubbia has taken a strong interest in the field of energy in general and in thorium in particular. Of course, you know he invented the energy amplifier. He conducted experiments at CERN, FIT and TARC to validate the ADS concepts. He proposed the NTOF facility, which is running today and which is still unique to these days. As president of the Italian Energy Agency, NEA, from 1999 to 2005, he promoted a novel method for concentrating solar energy at high temperature. And since June 2010, he is the scientific director of the Institute for Advanced Sustainability Studies in Potsdam in Germany. The title of his talk is A Future for Thorium Power, ? I would like you to welcome Senator Carlo Rubbia.
Ça marche?
Yeah.
Okay, thank you so much for all these kind words, which certainly I don't deserve. Let me get, I don't understand how this damn thing works here. How do you go do it? This is, Jean-Pierre, tu as une minute, s'il te plaît? How do you move it forward and backwards? This is, what is this nonsense? Oh, you have it there, very good, fine, thank you. Thank you, here, okay. Thank you, so let me get started with this discussion. And let me go back to the very nice presentation, very deep presentation of Hegi, which has described many of the points which I will try to come to mention. And let me start with this business of present nuclear energy, and especially the recent Fukushima accident. After the previous warning of 3 Mile Island, we should not forget that the second thing, has brought to sudden arrest one of the most advanced and heavily nuclear energy exploited countries, creating a strong movement against the continuation of nuclear power. This has proven the inadequacy of the present probabilistic concept, vastly used by the nuclear community, and the necessity of an entirely new, alternative, deterministic approach. In order to be vigorous and continuous, nuclear power must be profoundly modified. New breeding reactions based on tritium, natural uranium, or thorium, and which may last for many thousands of years, far beyond fossils, must be pursued, but with much stricter safety and deterministic level. The long-lived waste problem has to be solved. For such a new processes, a distinction between renewable and non-renewable energy is purely academic. Amongst the various breeding alternatives, the use of thorium represents a unique opportunity. This is a very old idea, strongly supported by the main fathers of nuclear energy, like Alvin Weinberg, Eugene Wigner, and Ed Teller, but perhaps then also ultimately neglected because of the intrinsic absence of military fallouts the use of thorium deserves nowadays a considerable attention. Now, today's nuclear energy is based on the highly fissile uranium-235, which is well known to be present at 0.171% of the natural uranium. Nuclear reactors, ordinary nuclear reactor, may operate either directly from natural uranium, CANDU type reactors, or more often with the help of uranium-235 enrichment, leaving behind depleted uranium tails, typically a 0.5%, 0.25%. In both alternatives, a substantial fraction of uranium-235 remains unused, and in practice less than 1 part in a few hundred of the natural uranium is actually burnt. The burning is somewhat extended with the help of producing plutonium-239 or from the uranium-238, in particular with the introduction of the so-called MOX fuel, in which the plutonium is extracted, reprocessed, and mixed again with the enriched uranium. These procedures reduce significantly, typically by over 30%, the consumption of uranium, but increase several times the amount of the minor actinides, or the spent fuel, and the residual, long-lived radiotoxicity of the waste. Now, although the exact amount of exploitable ores is not exactly determined, and depends on the lowest level of the recoverable uranium, as long as uranium is used in this way, and at the present level of consumption, which is 6.5% of primary energy, there are probably no more reserves of uranium than of oil and gas. Particularly interesting and so far largely unexploited are other fission reactions, in which a natural element is first bred into a fissionable one. And there are 2 of them that you well know. The first one is a thorium cycle, in which thorium becomes uranium-233, and then fissions in the closing loop. And the second possibility is uranium-238, which it goes to plutonium-239, and then plutonium is fissioned back again with 2.5 neutrons emitted. These sources of energy available for exploitable ore are comparable to the one from the very large, comparable to the one to the fusion reaction, deuterium-tritium, ITER, which is indicated here. Another breeding reaction, lithium plus neutron going to tritium, and then tritium becomes a source of fusion, tritium to deuterium, giving you helium plus neutron. The real question is, of course, how much thorium there is available. Thorium, the thorium-232, a pure isotope, unexploited energy resource, is about 4 times more abundant than uranium on the Earth's crust. While most of the uranium, however, is dissolved in the seas, thorium is present as mineral deposits. The total abundance is estimated to be 1.2 10 to the 14 tons. Soil commonly contains an average of about 6 parts per million of thorium. The monazite black sand deposit, which you described, Jean-Pierre Revol just described a minute ago, are decomposed by from 2 to 22% of thorium. Thorium can be extracted from granite rocks and phosphate rocks deposits, rare earths, and tin ores, coal, and uranium mines tailing. Estimates of the available thorium resources vary widely. The 2007 year NEE publications, Uranium-207 Resources Production and Demand, gives only 4.4 10 to the 6 tons of known and estimated thorium resources, but this still excludes data from much of the world. For instance, with well-designed thorium burners, the whole 2007 electricity production of China, which is 3.2 trillions of kilowatt hours, could be produced with simply 443 tons a year of thorium, uranium-233, a few percent of the rare earth domestic Chinese production. There are many different sources of thorium which show how rich thorium is. Let me give you some of the examples which are not meant to be the real source, but they indicate how easy it is and how different could be the source of thorium. Ashes have been even suggested. It has been suggested that thorium could be extracted from ashes from coal plants. And let me give you some example of how this is important. A 1,000 megawatt electric coal plant generates about 13 tons of thorium per year in its ash. 1 ton of thorium can generate, in turn, 1,000 megawatts electric in a well-optimized thorium reactors. Thus, the ashes of a single coal plant can conceptually fuel 13 thorium plants of its own power. So you should not use the coal, you should throw away the coal and take the thorium out of it. soil commonly contains an average of 6 parts per million of thorium, with energetic about 6 million times the one of coal. So if burned in a reactor, the thorium in soil will generate 6 10 to the minus 6 times 3 times to 6, 18 times the energy of the same amount of coal, as I said, indicated before. Therefore, recovering 1 in 1,000 of all the thorium on the crust, which is the crust, as I said, is 1.2 10 to the 14 tons. It's equivalent to producing the total primary world power, which is today is 15 terawatts, with simply 6 kilotons per year, 6 kilotons per year of thorium during about 20,000 years. I think in order to show very clearly the difference between oil, natural gas, coal, and uranium, you can look at this diagram here, which gives the global energy resources in zetajoules for oil, conventional, unconventional total oil. You can see the indicated there. If you have a mark, somehow you can get this thing going like this. I mean, can you get this sign? Here we go. Yes, you see there. Yearly consumption is indicated there. Resources are indicated there. And the consumption until use already up are these things. You can see clearly that there is more oil now sitting underground than there is already been used. So in fact, it means that there is plenty of oil for many, many years to come. Natural gas is likewise. Coal is there. Now, the important question is the total fossils indicated there are indicated down here. You can see this 281 zettajoule available. But this has to be compared with uranium. And now here you can either choose uranium used as a thermal reactor, and which is quite small compared to that, as I mentioned. If you go down, however, to use the seawater, then this number becomes very big. When you go and get it out, you get the seawater, the uranium out of the seawater, a few parts per billion. Or alternatively, as a breeder, if you go to uranium-238, then you have a much more significant number, 434 with 12,000 of water. But this is all to be compared with the situation of thorium, which is all in there in the rock, and represents something like 1.3 million zetajoules. So you can see under those numbers the absolutely preeminence of thorium as a source of energy for the future of mankind. Okay, conclusions. I have many conclusions. There's only one conclusion, of course. So the reserve of thorium represents an attractive potential energy supply for many millennia to come with little or no CO2 emissions. For instance, as I said at the beginning, the total electricity of China could be produced for 20,000 years with the reactors, thorium, with a million tons of thorium available. Now, let me go and now compare the differences of various fissionable nuclei and get a very simple comparison between uranium-235, plutonium-239, and uranium-233. You can see now in this table, first of all, the fission. Then you have the capture value. Third, you have the ratio of the capture with fission. And finally, the most important number is nu, the number of neutrons for fission. And then you can calculate also the number of neutrons per event, including not only fission, but also capture. And you can see the preeminence in this situation of thorium, of uranium-233 over the other element. And the other important factor which favor uranium-233 over the other systems, uranium-233 is rather insensitive to neutron energy, alpha and eta. Uranium-233 is the best fissile isotope in the thermal range. You can see here that 9% or 12% are the ratio capture with fission, and this is a very important number. The thorium of uranium-233 has practical potential for breeding over the whole neutron spectrum. As you can see in the column, last column, you can have thermal and fast. 3 different spectra has been considered and will be the discussion in my presentation. Thermal or epithermal neutron between 0.1 and 1 electron volts. Over the resonance region, in which you will go in neutron's energy between 10 to the 3 and 10 to the 4 electron volts, and then fast, which goes from 10 to the 5 to 10 to the 6 electron volts. Instead, as you will see in a minute, uranium-239 plutonium breeding is operable only with fast neutrons. And then let's be more specific. Breeding reaction, besides being almost unlimited source of energy, require, however, a major new development. Since 2 neutrons are necessary to close the cycle, one to make the material to be bred, and then the second one to transform the bred material into neutrons. Eta, therefore, has to be larger than 2. Now, you can see here the graph showing in this diagram the 3 different possibilities. You can see there the possibility of uranium-233. You can see here, this is thermal energy. This is eta. Sorry, let me go a little further here. Let me show you. This is eta equal 2. So the event is important if it has to be larger than 2. So you can see down here that uranium-233 is the only one which can do it. Then we go into the resonance region, which is somewhere in there, in which both uranium-233 is dominant over the other 2. And then you go up to very high energy, fast energy neutrons, in which you have, of course, both uranium-233, which rises up, and plutonium-239, which come there. This represents what I said, that the plutonium can only be workable at high energies, at very fast transport, while uranium-233 is available in a number of different possibilities. To give more specific, with graph here you can see several alternatives are possible for thorium-232, uranium-233. For instance, you can go thermal. This is thermal 900 Kelvin. Then you can go fast. You can see there the distribution on the other side. You can have a resonance region as a possibility, again, for thorium-232. And that allows us to use molten salts in that region, which I've indicated there. Then there is a liquid sodium with that value, and eventually a liquid with lead up there as possible alternatives. Now, instead, in the case of plutonium-239, you are bound to go to fast process, because only fast neutron is a possible reaction. Enrichment is no longer necessary in these systems, since they consume entirely natural material, either thorium or uranium. Enrichment is very complicated, expensive, and difficult procedure, which gets eliminated. And also, the second point, they use the whole totality of the material, and while the uranium normally uses only a smaller fraction of the uranium-235, so the energy is 200 times larger than the one currently available, only using the uranium-235 isotopes. Now, let me go a little bit historical situation of uranium, of the development of thorium. The early attempts were made in the very early times, and you can see here they go back to the golden days of the 60s, in which the idea was to blend a uranium-235 reactor system, add some more thorium with it, and therefore blending thorium and uranium-235. You can see a large number of possibilities which are described here, many of which are small, large, and there have been quite a development in this particular case from this kind of point of view. In these programs, thorium is a secondary uranium-233 producer with a repeated addition of external fissile material using 235. So it's a mixed thorium-uranium system. When uranium is over, thorium will no longer be usable. Now, this is in practical various solutions which have been discussed for such possible alternatives, and let me mention 2 of them which are relevant, which have been discussed in the past. One is the Radiotoxicity reactor. Now, everybody knows who Radiotoxicity was. Radiotoxicity was the man which invented the fundamental pressurized water reactor, which now is used universally in ordinary reactor, at the time in which Rickover was in charge. General Rickover was in charge of those things. At that time, he was in fact the one which developed the system for nuclear submarines. Now, Radiotoxicity actually died a few years ago because he died at 102 years of age, so he had a remarkable existence. And he is also well known for having a love for thorium, and he was producing a thorium-uranium blanket, which is indicated there. The second possibility is some attempt to do a CANDU reactors, but CANDU heavy waters with a thorium blanket associated with enriched uranium and maybe plutonium core. This technology is similar to the one that Radiotoxicity had developed. As Bernard continues, the newly created uranium-33 picks up an increasing greater share of the fission load. In practice, between 30% to 50% of the energy comes from thorium, and the rest is coming from uranium itself. Now, of course, the real hope is to make a pure thorium thermal breeder, a breeder in which only thorium participates from A to Z. This is essentially also, as I get an old idea, there are two important people which contributed to this. One is Alvin Weinberg, and the second is Edward Teller. Now, basically, the thermal breeder is drawn in this picture here, is represented here, a simplified diagram from a Fuji reactor, is a combination of a liquid fuel, which is made out of lithium, beryllium, and a fluoride of heavy metal, where N is either thorium or uranium, and which contains somewhere between 6.5% to 20% of thorium or uranium. The volume of this reactor is substantial. In order to get a reactor, 20 cubic meters. Temperature is the temperature of this Flibe, which is 630 Kelvin. The power of this identified reactor is 1 gigawatt electric. And the problem with this is that the molten salt reactor fuel is continually reprocessed by an adjacent chemical plant or line. This is absolutely necessary in order to make the thing work. And the salt has to be reprocessed every 10 days to ensure criticality. Now, there is a very complicated process here, which I'll very quickly deposit. The fluorine removes uranium-233 from the salt. A molten bismuth column separates protactinium from salt before decay. A fluoride silts them, distill the salts, and the thorium salts must be separated from the fission fragment, which are the waste. So we have a situation in which this is to be added. Now let me show you this story. Of course, this story was discussed many years ago in the MSRE experiment, molten salt reactor experiment, which is a well-known milestone of a pure thorium reactor. This thing was developed in the early 60s, and it was operated for 5 years without incident. Everybody knows, I suppose, about that. There is a combination, as you can see, of a nuclear reactor and a chemical power plant. Now, there was also a project called the MSBR project, which was presented to make a real big-scale reactor, 2 gigawatts with 1,000 megawatt electric. Such a design, you can see here, is being put together, but was stopped, as I said, in 1976 in exchange, of course, of the other alternatives. Let me just simply mention here very briefly the complexities of the reprocessing facility for extracting this thorium. You can see here the uranium is recovered. Then you can see the protactinium decay from residual uranium recovery, TRU to waste. And then you can see TRU extractions and metal extraction transfer. You can see that it's an extremely complicated process which has to be done continuously online. This is something similar to what you want to do with fusion. Also in fusion, you have to do the same thing, except there you have to use tritium to separate the single state of the other solution. The second story is coming from Teller, and Teller fuel reactor is described here and is using molten salt technology. You can see there, there's lots of features in this reactor which are worth mentioning. The first feature is that it's underground. You see, this is a rock underground, so the system is down there. This is the unit. And then the heat is produced here. It comes up to the surface. You can see this is a molten salt device in which, in fact, the fuel and the uranium and thorium are mixed together. Here, for some reason, there is no use of a cooling station. This paper was written by Teller 1 month before his death. And he wrote something which is worth mentioning. This is 2005. Let me mention to you what Teller was saying. The power plant could operate for up to 200 years with no transport of fissile material to the reactor or waste from the reactor during this period. Advantages that include the utilization of an abundant fuel, inaccessibility of that fuel to terrorists or for diversion to weapon use, together with good economics and safety features such as an underground location, will diminish public concern. We call for the construction of a small prototype of thorium burning reactor. This was done in 2005. Let me remind you that our work was already done quite before, because we had done the work on the CERN activity was done in the late 90s. So, but Teller continued to repeat and to sustain these kind of ideas. I think this is important. This was done, as I said, only 1 month before he died. Now, not all these assumptions are really true, but actually the idea is tantalizing. So let me come back on the conclusion about thermal breeders. The main advantage of thermal breeders is technology is well known. You can see here, for instance, the behavior for graphite of uranium-233, which is 8 larger than 2. And this is the only thing possible because the other processes, plutonium and uranium-235, do not reach the breeding equilibrium. Theoretical breeding ratio is given here for an ideal number for an infinite-size reactor, a variety of coolants and not fission products. You can see more detail there what happens if you do the plot for, for water, heavy water, and carbon. You can see here that with the appropriate ratio between the coolant and the fuel, you can get something like the branching ratio of the order of 1.2 in the optimal condition for any of the three solutions. So this is possible to construct either a D2O or H2O or carbon things in this region with a number there. However, many other effects reduce the breeding ratio, and the delta L is a change, relative change of the breeding ratio. For instance, we have to add the Poisson fraction in thermal reactors, which for a density of a relatively low density, like used by Weinberg, of 3 megawatts per kilogram, is giving a reduction in L of 4.7%. Then you have losses to the intermediate PA233 capture, which is protactinium is suppressing the uranium-233 because it kills it, and that gives another change of about 0.1 in L. And the third effect is also you have to add into there fission product built up, and then you have to add also the fact that when you continue to run the system, besides to a uranium-233, you produce uranium-234, and uranium-234 has not less relatively fissionable. So the theoretical assumption of branching ratio 1.2 is essentially disappearing because of that factor, xenon Poisson. The most important one is protactinium-233 captures, and so forth and so on. And therefore, this is why you need necessarily to have the reprocessing. In fact, the conclusion for a pure thermal thorium operation, a thermal neutron reactors with hydrogen, deuterium, or carbon coolant require inevitably a delicate online fuel reprocessing in order to provide satisfactory. And these are two possibilities for that. In a critical reactor, without such a chemistry, the small k excess greater than 1 will be quickly wiped out by the presence of the fission product, fluid cladding, and so on, as I said. In comparison, an ordinary CANDU, which is the lowest k infinite possible, is K0, 1.47, and while we are now here to something like 1.1 or 1.2 for the case of thorium, so it's too small. Now, you can say, why not making a subcritical ADS, thermal subcritical ADS? So we make a subcritical ADS with a proton-driven, K less than 1. But then you get another problem, because the active size of the fuel around the beam is proportional to the inverse neutron cross-section times 1 over 1 minus K. And therefore, for thermal neutrons, the cross-section is large, and therefore, the fission activity is narrowly concentrated exponentially around the location of the target. Therefore, the beam-activated volume for the fission energy production, even in the thermal ADS, and for reasonable value K0, is strongly localized and not very uniform. So it's not easy to make even a subcritical system as a thermal unit, just because of the fact that the concentration is very close to the proton beam, and it does not allow you to construct a uniform filling of a critical mass. So conclusions. The thermal thorium configuration demands a complex, flawless, and risky online reprocessing of fuel in order to remove the fission products and protactinium-233 captured prior to the formation. The liquor reprocessing produces an additional strong radioactive background to the delayed neutron and gamma emissions generated outside the reactor core. There's another phenomenon. Your system, which extracts the various material for reprocessing, is also carrying some neutrons with it, because there are delayed neutrons and gamma emissions, and therefore not only the reactor is going to be very radioactive, but all your chemical plant will be super radioactive, and you have to solve a problem with it. Now, it's unlikely such a technology may become widely acceptable, especially in view of the presently very sensitive, critical public concerns. So the problem of thermal thorium reactors have a lot of problems, which seems to be quite serious. Then, this is why has been created another point of view, which in fact is CERN related, already in 1995, which is called the thorium-driven fast energy amplifier. Let me briefly describe what is this situation is. The drawing is there. Many of you already know it. It's a subcritical system given with proton accelerator. Fast neutrons in fused cycle are based on natural thorium. This is a closed cycle. Actinides are recycled indefinitely, the waste are fission fragments, and the structure and material which are relatively short-lived. Lead as a target, both as a neutron moderator, as a heat carrier. Deterministic safety with passive element to eliminate criticality. This is a subcritical system. Meltdown, there is no meltdown possibility. Decay heat, and seismic protection. And this is essentially what was the key to this process. Now, let me show you here how it is coming along. You can see here an accelerator complex which produces a beam into a fast-driven energy amplifier. I've shown here the more recent description by Aker Solutions, of this device. And you produce there the energy through a standard turbine and power generator. After 10 to 15 years, you make a fuel discharge. The fuel discharge produces a spent fuel. The spent fuel is reprocessed and refabricated, adding the fresh thorium supply, and it is coming back into the cycle again, except that the fission fragments, which are packaged as a waste, and then put to the circular deposit, they disappear with that. That's the basic idea behind all this. Now, here I have all the parameters, which I will not have time to describe you in detail. Now, this idea was developed very recently in 2010 by a feasibility study by Aker and Solutions company in England, and this is we have what has been developed. It's very similar to the original descriptions. The power is the same, and you can see the characteristic here, and you can see how it's constructed. This is a very nice design, which is perfectly feasible to my view, and it's very nicely and well designed. So we have a feasibility study already available on that. And of course, the same system can also be modified as a minor actinide burner for ADS, which is no doubt will be discussed by other people during the conversation. Now, let me stress the alternatives here between these various alternatives. Suppose you want to continue to generate the power 1 gigawatt electric for 1 year, then you have to need 3.5 million tons of coal. And that will represent a significant impact on the environment, especially for CO2 emissions. And now, if you go to an ordinary power reactor, you need 200 tons of uranium, low CO2 impact, challenges to reprocessing, long-term storage, hazardous waste, proliferation, and enrichment. Now, the solution of the fast thorium-driven energy amplifier solution, this is described by the Aker solution here, is 1 ton of thorium, low CO2 impact, can eliminate plutonium radioactive waste, reduce quantity of much shorter duration storage, hazardous waste, there is no enrichment, no proliferation. So the advantage of this thing is extremely nice. Now, let me show you here some of the characteristics of this number. Now, let me look at the numbers for a practical situation. So let's take 1 GeV, 1.5 GeV thermal power. You can see here, we start from proton energy. We need 2.7 10 to the 20 fission per second if we do a K equal 0.997 with a gain of 700, as we do in the last developments which we have done together with Aker Solutions. There are in there 3.8 10 to the 17 spallation neutrons, 30 neutrons for every proton. There are 1.3 10 to the 16 protons per second, which are accelerated. So to make this power of 600 megawatts electric, 1.5 gigawatt thermal, you can need a current only 2.2 milliamp per 1 GeV, which corresponds to 2.2 megawatts, which is perfectly feasible within the state of the art, as will probably be discussed by some people here during the next days. So the accelerator is perfectly feasible, and so forth. Now, the loss in the number of captured reduction in efficiency is indicated here is substantially as follows. You have coolant lead 6%, cladding 3%, beam window is a little bit, then you have main vessel effects, then you have leakage and so forth. So the conclusion is that due to fission product linearly growing with burn up, to the final delta L will be 0.06, including also buckling changes due to reduction of fuel mass. You can see here is a graph. You can show here the burn up in gigawatt Dayton indicated there, and the neutron fraction reduction. You can see that, in fact, you can go essentially up to 120, 130 gigawatt Dayton, which would correspond roughly to 10 to 15 years operation with no changes inside the sealed container. That's a great strength of this operation compared to the case of the thermal power descriptions. Now, let me also mention the comparison between the basic ideas of this project, which is based on the energy amplifier, can be either subcritical or critical thorium breeding nuclear reactor, is essentially considered to be indefinite repetition of very long-lasting, nearly identical breeding nuclear fuel cycle, progressively approaching to an equilibrium concentration configuration generating uranium mixture. And such a specific configuration, which I discussed now very briefly, is called secular configuration. It's characterized by an extreme fuel stability during a very long duration of the cycle, in particular extremely constant spontaneous neutron multiplication coefficient, as you'll see in a minute. Each cycle is lasting from 10 to 15 years, determined by the integrity of fuel materials and to radiation damage, DPA, displacement per atoms. Now, the basic features, let me show you here. Let me mention to you, first of all, there is a breeding equilibrium which is being described here, which is very different, which is very small for thermal neutrons, Xi is 0.1%, and very large for fast neutrons. So about in fast neutrons you need the amount of uranium over thorium, which is considerably higher for fast neutrons. The breeding equilibrium is shown here. If you produce something above the breeding equilibrium, then you go into the line which comes down. And if it's less than the breeding equilibrium, you build up the ratio, and after a certain burn up, you end up to these magic breeding equilibrium conditions. And the fact is, let me show you these things in these conditions. Actually, we have developed something a little bit more sophisticated, which we call magic equilibrium for breeding, in which what we do in here is we make a magic cancellation between, the one hand, as you see in the graph, is the fact that, first of all, let me explain you. First of all, the fresh thorium to recover uranium shift the K below the breeding equilibrium, because you have after the spent fuel is recovered, and therefore the K will grow up as a function of build-up in the line. It's a green line due to the build-up of that phenomenon. But then, on the other hand, we have fission products which will reduce the multiplication coefficient with distance, and you can see that the two things cancel. So in a proper condition, you can have that the buildup of uranium-233 is exactly compensated by the fission product emergence, and the result of the two gives you something which is extremely constant, and it stays constant within about 1% over 10 to 15 years. Here you find a graphic image of that situation. You can see that the delta here is 1%. 1% changes in K. And you see that it goes all the way from here to there, and it goes from 0 to something like 120 gigawatt Dayton, which is something like 8 to 10 years of running time, because of this cancellation coming from the magic equilibrium, which was used in our case. Now, let me show you that in a more detailed way. You can see here a graph which shows the process of constructing and using an energy amplifier as a function of time. At the beginning, we start with initial fuel, which is MOX, standard MOX, which is made 85% of thorium oxide and 15.5% of plutonium oxide. You can see in that graph the beginning. You see here the situation of the plutonium coming down and the buildup of the uranium-235 coming up. And the combination of the two is occurring as a function of time. The more time goes by, the more you see the initial MOX disappearing. You see it gets very small after so many time, while you have a constant buildup of uranium isotope. As indicated there, you can see here, sorry, what's going on here? I lost it. You can see here
that in fact you can see here that all the U's are in there, uranium-33 is there, all the plutoniums are there, and this is plutonium-233 production. You can see there, therefore, there's a smooth transition all the time from the initial production of a MOX mixture to the construction of an indefinite production of based on thorium. The important question here, of course, is the question of the K. You can see here in the same diagram, 1 to I, K L, the effect of the number for the K effective excess, which you see is something like initially 4%, and you see nowhere along the line you go below a few percent of excess in criticality, which is used in order to operate the system and make it essentially subcritical. You can see this transition between the situation in which you start with the MOX and plutonium down to the situation when you have a pure thorium is absolutely smooth. You can see there how constant the K is over the 150 gigawatt Daytona burn-up, which corresponds to many years of functioning. And therefore, the transition from plutonium to asymptotic thorium-uranium mixture is absolutely constant and very credible. This is actually calculated with precision with the evolution of this energy amplifier, which I have described in the beginning. So it's the upper limit K equal 1, of course, is then adjusted with the help of control bars, so to be able to reduce the rate and make it slightly subcritical, as we said. Now, the overall situation, of course, are many. The most, as I said, the basic solution of this energy amplifier is an interrupt operation about 10 years, in which they only waste fission fragments. The radioactivity of the material is intense, but limited with time. You can see a graph which shows you an ordinary reactor. Here is something which is extremely interesting. You have an ordinary reactor here, pre-RW coming out from origin calculation for one same power. Here you can see the energy amplifier. And you have, of course, here is the alternative of magnetic fusions of various types. Here is the radioactivity of coal ashes, which of course need no protection. And you can see that essentially after a few hundred years, when the decay of the fission fragment is being decayed, the remaining radioactivity is of the order of coal radioactivity, so it's perfectly legitimate. So this thing can come back into the environment after a few hundred years. And look at the enormous difference between this and the situation in an ordinary reactor. Now, this plot is done in linear paper. In linear paper is the real paper where we live. It should be the kind of paper you should use for this graph, not logarithmic paper. Actinides are recovered with no separation. The seeds are, after topping about 10 to 15% of first breeding element, thorium, in order to compensate for the loss of the element. A small fraction actinide is not recovered, end up in the waste. This is taken into account. And the cycle is closed in the sense that the only material inflow is a natural element and the only outflow is the fission fragments. So conclusions, a pure thorium breeder may operate in a variety of configurations according to various numbers. However, the basic chain reaction will converge to a breeding equilibrium, namely to steady conditions in which each fission nucleus is replaced by newly bred 250-year nucleus, and simply the operation consists in adding periodically thorium supply, and ideally the process is closed. In other words, you produce thorium and you get up fission fragments, which decay with a very relatively short lifetime, and nothing happens after a while. Now, few questions. I have another 10 minutes to finish this thing. 11:30, you said. 10:30, yeah, 10 minutes. Yes, fine. Proliferation issues, I think this is an important thing. There are three main elements in the proliferation issues which have to be worried. Uranium, neptunium, and plutonium, plutonium-238. Now you can see here the diagram which shows the situation. You can see the bomb-grade plutonium-239, the uranium, neptunium, and plutonium-238. Here is indicated the critical mass in kilograms. The decay heat of the critical mass in watts. You can see that, for instance, plutonium will give a very hot material. Uranium will give you, 233 will be medium, comme ça, and while the bomb-grade plutonium and gamma activity will be huge in the case of uranium thorium effect. This is 1,300. These are curies per for critical mass. You see it's very known. And the neutron yield also is very important, which, for instance, kills the neptunium, because there are too many neutrons. You get a fizzle factor, which makes the situation unacceptable. Now, you can see here what will happen if you were to use uranium-233, and critical mass of uranium-233, which is 28 kilograms, and you, after asymptotically, and you have, you put them at, in that material, you have thallium-208, which produces a very strong gamma rays, 2.6 MeV, and a reasonable walking distance, you will be reaching the lethal dose after 10 minutes. That's clearly something which you will not be able to use under normal conditions. Now, the long duration of the fuel cycle permits to keep SEAL under international control, of course, avoiding lethal insertion of any other possible bond-like materials. But the point is that the proliferation seems to be quite strong. Anti-proliferation measures can strong, combined with the fact that the fuel cycle is closed, possibly under EA control. It might be possible to do this thing in a very safe way. Now, in the construction of the system, 3 possible materials were described here: lead bismuth, and sodium. And let me show you here a graph which shows the situation. You can see here the 3 possible alternatives: bismuth, lead bismuth, eutectic, pure lead, and sodium. You can see that initially, this you see the ingestive radioactivity as for the our energy amplifier as a function of time, and I put the time going up to 10 years. You see that initially the situation of sodium at the beginning, it's worse, slightly worse than lead, but then with time, sodium and lead have roughly similar ingestive radiotoxicity. As you can see there, down below, you see subdivision by isotopes. But you can see, on the other hand, that the situation of the lead bismuth, because of the presence of essentially of polonium, is absolutely disastrous. You can see here, down there, the situation of you see there the situation of you see the situation of, excuse me, something crazy here. No, just a moment. You can see the situation here. You can see that, in fact, you see that we are here with the emissions is about 10 to the 11 sieverts going on for a long time, up to a year. And while here, the sum is about 10 to the 8 sieverts going on in this particular way. And it's about 10 to the 6 sievert, and it goes down to this, and this sodium is slightly smaller. So, in fact, you can see that the PBL tactic is a major issue, which will be very difficult. The second question, of course, are also the corrosion studies, which is an important question. This is the work which you've done together with KIT and ENEA. You can see that, in fact, as a function of the temperature, there are various alternatives, but it's quite clear that lead and LBE, lead is there, LBE is shown there. It's quite clear that the LBE, it's lead bismuth, is quite acceptable at all temperatures, while lead may have some problems associated with the corrosions and phenomena like this, which becomes very important, which are very important. 750 degrees, you're completely out, everything is red. It's probably acceptable up to 600 degrees, but it remains to be discussed. This is a very question. So essentially, we have a lot of experience from Russian activity of lead bismuth molten mixture, but I mean the fact is indicated down here that polonium is extremely important. By the way, notice the presence of air. 50% of the polonium-2 is volatilized in 24 hours. Although there are some hopes that it may work, it has to be proven. So it is concluded the pure lead is highly preferable. Lead bismuth should be excluded for any wide commercial avoidment. So I think you should really go to lead finished. So conclusion, a fast metal called IASS may represent a practical solution to the exploitation of pure thorium breeder. A detailed design based on CERN AT9544 has been completed by Acker Solutions, which has done a proper job of designing the technology on the basis of our physics, which we have done before. The metal coolant can be a priori sodium, LBE, or lead. However, problems persist since sodium is highly flammable. LB is plagued by a very large amount of polonium activity. Lead is far less radioactive, but it needs higher temperatures and may be plagued by corrosion. So there is still, although the problems are much less than thermal reactors, there's still some problems there. Now, let me also mention another fundamental questions. I will use some more minutes on my presentation. Well, whatever is required. And if you want to stop me, I'll stop it. I mean, you have other, so forth. No, we need a little more than 5 minutes. I'm sorry. I'm sorry for you. Now, working on neutron resonance, neutrons for fluoride, salt, and graphite are thermal. And essentially, the other possibilities go to a situation in which you are in the resonance region. This is obtained by in a very simple way. Let me show you how you do in practice. This has been done by lots of people. It's a very nice idea, and removes the reprocessing. It's a subcritical operation. High proton accelerator is combined in a system where there is little or no thermalization. So the neutrons are fast, as they are shown in the previous graph here. They are very fast. You see here the spectrum for a fast neutron, and they're fast with molten salt. And under those conditions, you can see here that you can construct a system like that. This is essentially, you have a beam of proton which goes directly into the liquid. This is molten salt, which contains simultaneously the uranium and thorium, and contains also the other fluorides. And this system is circulating with a heat exchanger and a pump in a very simple way. And the neutrons are less intense. They're only 15 per proton, but still significant. And they are operating, the system is, of course, much higher in temperature. And there is a lot of information which is still there, which tells us that the Hastelloy end proven is compatible with fluorine salts. The heat exchanger is a standard LIBEF. And essentially, it's simple and cheap to build. And there is multi-containment against leaks. So it looks like this possibility is a very interesting possibility, which is worth looking as an alternative. Now, the molten salt is drained and reprocessed maybe every 150 gigabyte per ton. So this is still a molten salt system, which doesn't need any online chemistry reprocessing because of high energy. Now let me also very briefly mention that, well, let me skip this one because you have other things. So I would like to spend my last 5 minutes in a new reprocessing method because I think this is a very important question. Reprocessing. Reprocessing is the key element behind this energy amplifier, but the new reprocessing methods are necessary. At the end of cycle process, in the case of thorium, needs a major development and deserve new methods. It would not be appropriate to throw away every time the seeds. We shall miss the indefinite repetition of very long-lasting thorium fuel cycles. But the standard aqueous process, Thorex, Purex, and so on, applied to thorium fuel, in which actinides are separated and further recovered in a centralized reprocessing facility, are presumably possible, but certainly both very complicated and costly. So I don't think Thorex and Purex is the right solution to go with an energy amplifier in this particular case. Aqueous solution uses an organic solvent, which is easily decomposed, deteriorated in the case of closed thorium-uranium cycle, by the substantial effects coming from the large radiation damage. So we have a problem there. And the creation of a new appropriate end cycle procedure has been so far a disclosed necessity for the practical realization of any closed thorium cycle. And I'd like to spend my last minute to tell you essentially about how to use, according to me, you should be reprocessing. Here, now, there is one very important property that uranium and plutonium are the main seeds of the case of fast energy thorium amplifier. And the other interesting property is that they are volatility of fluorides is for plutonium and uranium is very strong. So initial UO2 is converted without fluoric acid to uranium and tetrafluoride, and then from tetrafluoride you go to hexafluoride. You can see the diagram in there. And the result of that, you go from the spent uranium seed out of oxide into fluoride with such a simple process. Now, then spent thorium, fission products, and minor actinides, protactinium, americium, etc., are considered waste. So you are not I just concentrate exclusively on plutonium and uranium seeds, and then new thorium is also used in every cycle because thorium is cheap, and this is the final transformation for fluoride in oxide is currently performed with the help of hydrogen. Let me show you here in this area what you do. You see the picture here. You come with a spent fuel in there. You have you wait for 6 months for the protactinium to decay. Then you make a declouding. You go through a fluorination, and the fluorination is producing uranium. You can see from here the fluorination is producing here plutonium hexafluoride and uranium hexafluoride, which goes down here, and all the other stuff comes down as a waste. So you only get out the plutonium and the uranium with a simple fluorination process. Then you condense, you volatilize it. Then eventually you go through a second process, which I'll discuss into a moment. But anyway, you go to electrolysis, and then you go back into put fresh thorium oxide, and you make new fuel. So you start with spent fuel here. You separate out the plutonium, uranium as the seeds. All the rest is waste. And then you go down to this process. You go from uranium to UF6, you go with water and hydrogen into oxide again. You add some fresh, you top it with fresh CO2, and you go to new fuel. So this is an extremely regeneration process with fluorination, which in my view could be done very easily in a spot. About 90% of the deposited uranium produced to date is stored in uranium hexafluoride in steel cylinders in open air yards close to the enrichment plant, so this process should be perfectly possible. Now, let me show you the toxicity diagram, which is absolutely key question here. You can see here the way in which the radiotoxicity goes. You can see here that you have essentially the fission products indicated there, ingestive radiotoxicity functional time. You can see here the main question here is the fission product which come down to this point here. And if you are maintaining the protactinium in here as this is protactinium which is used as waste instead of being recycled. It gives you this kind of background. And then there's also some thorium. We give you thorium 230, it goes there. If you remove these two, as you'll see in a minute, with a simple process, then you're only left with the 0.1% of uranium, 2% of plutonium. That means that essentially the situation after the end of the fission products is essentially dominated still by the fission product. And these two actinides there are giving a very small, this is curium, this is americium, and these are the other factors you can show you to give you a very small effect. So the real question is, either you just forget about it and you run with protactinium there and thorium there, and you add them and you bring some radioactivity there, but you can gain 3 orders of magnitude in emission just cleaning up this simple 24 kilograms of protactinium and 22 kilograms of thorium 230, and you'll show you how you do it in this guy over here. This you do essentially with the long-lived protactinium, which can be recovered with the help of bismuth. Bismuth can be used in order to take the protactinium out. And the radioactive, this gives you away the 231 protactinium. The discharged thorium contains thorium-230, maybe fully recycled seeds with appropriate chemical instructions. This is the second possibility. And therefore, the remaining seed is essentially waste, uranium leaks, plutonium leaks, americium, curium, and the radiotoxicity, which is small or negligible with respect to the major fission fragments, so you solve the problem in a much simpler way than you do otherwise. Now, there is one more point here which I'd like very briefly to mention because you are pressing here. If you do a secondary process of fluorination just before creating new fuel, then you can find out from this diagram here that indeed all the decay products, which are the radioactive, can come to the waste, while after the fluorination, the uranium and plutonium are clean and therefore are not radioactive at all. So let me take some radioactive production with all the decay products in there and then go through a second local small size fluorination that will give us this thing with no radioactivity, and all the radioactivity go to the waste. So until such a radioactivity is built up again by secular construction, you have a clean situation, which you can very quickly transform into a uranium oxide, essentially with a process of separation, essentially in a condition in which the radioactivity is very low. So you can strongly reduce the radioactivity, vastly reduce the radioactivity of the system. You see it's a function of time here, the equilibrium contamination, which is very high at the end. At the beginning is when you go through a fluorination, because of the separation between the radioactivity and the uranium and thorium is very small, and therefore each cycle is expected to manufacture something like 15 pins, 9 kilograms each time, and this can be used to do the transformation under very simple conditions. In a manufacturing is done quickly, but in this case, the radioactivity is very small. For instance, after 5 hours after the fluorination, you have only 1 millicurie of radioactivity in your fuel rod, and it goes to 0.1 curie after 2.5 days, which is essentially something acceptable. It's an interesting conclusion. So let me now come to the conclusion. Fuel reprocessing or beta regeneration is an essential part of the thorium process. It's a fortunate circumstance that most of the seeds are uranium and uranium fluoride is a fluoride, and uranium hexafluoride is the most volatile compound known to exist. Also, plutonium hexafluoride is volatile. Therefore, uranium and plutonium are the ideal seeds for the breeding process, and all the rest, a simplified process can be consist of keeping all the rest, spent thorium, fission fragment, minor actinides, as waste, and just leave only the uranium and plutonium seed, and just make a simple fluorination to get these things out. Now, my own recommendations, then I conclude. A 6 megawatt prototype subcritical beam reactor along the line is acceptable, but I would not use a metal, I use a salt. So I will combine the process which you're doing with a fast reactor, but instead of putting lead, which is a metal, I use a salt. So I would suggest to replace in the design of CERN AT9544 and into aqueous solution a salt. Now, a fuel is a conventional structure. A fuel then becomes a conventional structure of stainless steel rods and metal oxide. I think the mixing together simultaneously the fuel and in the liquid, it's quite a risky solution. And so therefore, the fuel is a conventional structure of stainless rods and metal oxides. It operates high temperature, 640 degrees. All parts contacting lithium Lib are fluoride, coolant, and Hastelloy N is known to be compatible with this. The thorium is, this thing is run for 10 years, as I shown in the graph. In-situ fuel processing is performed based on transformation only of uranium and plutonium into hexafluoride, which is rather simple. Spent thorium, fission product, and minor actinides, americium, curium, and waste. Uranium and plutonium as seeds. Long-lived protactinium-231 is recovered with the help of bismuth. The discharged thorium is radioactive, since it contains some of thorium-230. So you have two choices. Since thorium is cheap, you may inject the new thorium each time, or you can be fixing it by recovering the presence of the background. Now, summary. The energy amplifier, especially when compared with fusion, has a lot of favor things: safety, credibility, availability, chemistry, waste disposal, operation, technology, proliferation resistance, a cost of energy. They're all, in my view, well understood and lower. So let me conclude essentially with a very simple graph, which I took from Sharpak. This graph shows le couplage d'un accélérateur et d'un réacteur nucléaire, un accouplement contre nature ou l'avenir de l'énergie nucléaire, the coupling of an accelerator nuclear reactor, a mating against nature or the future of nuclear energy. And with that, I will conclude. Thank you.
Okay, so we have time for a couple of questions. Not too many, because otherwise there won't be a coffee break, but please, could you bring a mic?
I don't understand your problem with timing. You said I should finish at 10:30. Today, okay. My number says 10:33, so I'm 3 minutes late. Am I correct?
Yeah, it's fine.
Yes, fine. So don't panic.
Okay, just 1 second. The mic is coming to you. This gentleman there.
I have a problem when you say that this.
So have I. Yes. Everybody else has problems. Yes.
Can I repeat?
Yes, please.
Thank you. I have a problem when you say that this kind of reactor is safe. I mean, the major problem of nuclear energy is the residual power coming from fission products. This was the case in Fukushima, in TMI. You have to cool the reactor. How this phenomena disappear in your reactor?
I think is one of the basic features of the of this EA95 paper, which I would suggest for your attention. The reactor is never is cooled here with essentially with air. You have there is also the same thing is done also by the Teller system. You have a swimming pool, or either a metal or if you like a salt, and this is sitting inside this container. And now, if there is some heat produced by fission fragments, as you mentioned, and if everything stops, there is no power, you're completely off, like you are in the case of Fukushima, then the heat will produce, will be cleaned up in this particular case by the fact there is a double layer in which air can circulate. So there's natural air distribution, which is occurring naturally in the system, because double layer inside the container has enough space so that the air can warm up in the cylinder and come up as a hot air, and this hot air is sufficient to keep the reactor stable throughout the process. So therefore, the answer is that by using this kind of configuration and using spontaneously present hot air, which is made hot by the walls of the container, such an air is sufficiently abundant to be able to dissipate away the heat throughout the process of decay. This simply means that this device, even if nobody is there, if everything is off, it will do nothing, but it will go through a temperature cycle and come out. If you read in that paper of ours, you will find also the way in which the temperature changes as a function of time. You find that the temperature is rising to a few hundred degrees and then comes back again. So the solution is perfectly acceptable. It's called AirVax system, in which air is naturally available to cool up, clean up the system in such a way that since you have a sufficiently high temperature in the molten salt and so forth, and the amount of air you have is reasonable. So therefore, the answer is extremely simple. If everything stops, the reactor will not do anything. It will just sit there and slowly, kindly, gently disappear with temperature in a certain period of time. So there is no meltdown, there is no problem of any kind, even without any intervention, even without any electricity, because the only thing you need is air. And air is available all the time. And this, by the way, is also present in the graph that Teller has put together. In the Teller graph, which I showed you in 2005, there's also the same AirVax story. So the AirVax story is a reasonable solution for this problem. It's a deterministic solution.
Okay, I think this is clear. Next question.
Hello. I have no doubt that we can construct a nuclear energy system based on an energy amplifier. But the question is not whether we can, but whether we should. You've said nothing about cost, or indeed about reliability of such a system.
You give me 45 minutes to go from A to Z, and you say you haven't talked about the costs. I mean, what am I supposed to do? Okay. I can tell you the costs if you give me the time.
About cost.
What?
If this is not cost competitive with other energy systems or with carbon-based fossil fuels, then we don't have a solution. So can you say anything about cost?
Look, first of all, I don't understand very well your statement because of a very simple thing. Let me say, of course, cost can only be done at the end of the analysis. With the people, with this meeting, this work which he did with the recent presentation, which he did with on the energy amplifier, the last description which I gave you, the 2010 work included all those values done by professional scientists working in nuclear power. So this is not my own personal view, it's a point of view which comes out of the presentation that we had in the second round based on our results. Now, the answer is extremely simple. First of all, thorium is plenty, is used very parsimoniously, and is cheaper than uranium. Secondly, there is no necessity of making reprocessing, enrichment, because that uranium is directly used, so the enrichment of nuclear power goes away. Second problem, you have the lifetime of the system much longer because you're burning things here of 150 gigawatt day-ton rather than the 30 gigawatt day-ton you normally do in a reactor. So you get longer expansion. This is, you don't have to stop with the unit as you do in an ordinary reactor for a few weeks every year in order to move around your rods and everything else. This completely disappears. So the maintenance separation of this reactor is much smaller than the maintenance you require for the other solution. Third question, if you take a reprocessing based only on fluorination, you can do it on the site, and therefore you can make something which is substantially cheaper than taking all your material and send it to La Hague and have it all separated out and done and so forth and so on. So there are very substantial factors which indicate that this process will eliminate many, many of the questions, and therefore the cost cannot be higher. But of course, in order to know what the real cost is, you have to build an engineering design if you don't have that. But a priori, we are saving a lot of things in here, which other people are normally using in reactors. And therefore, the chance is that we can do something which is certainly economically viable. The real question, however, about nuclear power is the hidden cost coming, for instance, from reprocessing. I mean, you know that no one knows how to reprocess the waste coming from nuclear power. You know that the situation on Yucca Mountain is now on stand. We have that many countries, Germany, Switzerland, UK, have estimated the cost of cleaning up the mess coming out of the nuclear power, and they get in phenomenal numbers because it takes many years, tens of years, and lots of money, and so forth and so on. And those costs apparently are not included in the original cost of the program. They are coming up because mostly paid by public money. Because as you know, in the United States, whenever you deliver the spent fuel, it's no longer the responsibility of the company to do it, but it's the responsibility of the United States government. And these kind of effects are, of course, something which are representing hidden costs, which are very large, very important in ordinary nuclear energy. With that system, we are not dealing with long lifetime. In a few hundred years, the stuff has disappeared, and therefore we go we go to what we call a secular depository. So even the problem to transform this material and reconstruct it in such a way that you can use it, it's much simpler. Also because the time which you need to spend in order to clean up your radioactivity is smaller. So that is also a factor which is saving. So when you go through the number of savings, it seems to me you have a lot of numbers which are there, which are saving. Now, from the point of view of the cost, the basic cost of constructing a system of rods, a fuel rod, if you put in there uranium, you put in there thorium, it doesn't make any difference. The cost is the same. All the fabrication costs are similar. The fact that they are using molten salt to cool the system is certainly cheaper than using sodium, and it's certainly simpler, and they also will save some money. Now, think how much money you have to spend if you want to have sodium from a fast reactor operating in terms of cost, of damage, and risk, and safety, et cetera, et cetera, et cetera. So, I mean, all those factors are indicating that thorium is a promising possibility. It has to be studied, it has to be understood, but a priori, I don't see any obvious cost in there which will make it out of range respect to many other things people are normally doing.
If I may add just a small thing, if you think that the issue is to make energy cheaper than fossil fuel, you should ask our friend in China, who have almost infinite supply of coal, why they are so concerned about burning coal, for instance. So I don't think the issue is to make energy cheaper than fossil fuel. I mean,
well, the cost of coal in China is a major problem anyway, for other reasons, because it costs in China to make 1 ton of coal is $100 because you have to get the coal on the ground. If you use coal instead from Canada or from United States or from Australia, the cost is much lower because you can take it off surface. And at present moment, the cost of imported coal to China is $40 to pay to the Australians to give you the coal and $60 to transport. It makes $100. And the cost today of producing in China with Chinese method coal is also $100. So now, of course, the cost of making that is also thousands of people dying every year. It represents a lot of difficulties. The cost will grow with time because of better situation. So the coal in China can be also a paper dragon associated with the fact that there's very little no coal in China which is coming from surface. Most of it comes underground. And many countries like France, UK, and others, which are more costly, they've eliminated completely such a production of coal in exchange for coal, which is cheaper today to bring coal from Australia into Europe than they go in Italy and get the coal out of Sardinia, and so forth and so on. And these kind of phenomena are important. So don't think the coal is obviously a financially attractive solution. There could be problems there which may also offset things. This is why they are very right to try to get other alternative to thorium as a possibility.
Okay, question there.
You want to be
Hamid?
Carlo, you showed us the K effective of the fast energy amplifier 997. And I think the reason for that is willing to limit the power of the accelerator to reasonable value. But do you think it's already optimized, because you know that we have to take some margins for the value of the K effective for some unforeseen phenomena for convection, etc. Do you think there is still work for optimization there?
Well, it seems to me that the problem, the question whether, I mean, look, first of all, I show you the graph. With thorium, our K is 104, 4%. Throughout the study of this complete cycle of the system, starting from plutonium, going down to uranium, you always have an excess. So there is always an excess there. I show in that graph, I suppose you noticed that. So there is an excess which allows you to go critical. Now, why should you go critical, or should you have an energy amplifier? This is a totally independent question. If you go critical, the control capability is less important than going subcritical, because subcritical stops, when you stop the accelerator, everything stops. In the critical system, you have a more complicated system, you all well know. Now, I am of the opinion that a subcritical system is advantageous because it allows you control, while the critical system is requiring an indirect control through other phenomena that you know very well, especially if you're dealing with a temperature coefficient which is the wrong sign. Then in this case, you're really in trouble with the reactor and you're no longer there with subcritical current. When you look at all those numbers, you realize that if you have 4% extra to go, and then you can reduce it to less than 1, why should be 0.98? Why should you have 2% of difference? You can, in my view, you can make it much smaller, it will still be okay. I mean, I am assuming there that, in fact, I can go to a much closer to the criticality, still staying below it, and this is an assumption. I mean, you may not like it, and you can do it differently. Now, if you do it something different, if you're doing thermal reactor, then you have real difficulty getting 1. But if you go with a fast reactor, you can get more than 1 already. So there are 2 solutions are possible. You can either go with a normal reactor, but then you have to have a negative temperature coefficient and all the problems, or you can put a small accelerator, baby accelerator, which gives you enough control capability. And it will cost just as much as it costs control rods, because control rods are also expensive. And if I look at the cost of control rods and the cost of a small cyclotron, like Mr. Mandrion will describe today after tomorrow, you will see that, in fact, the costs are very comparable. So in my view, I ask you my opinion. I say, I will make it subcritical. But I don't think it's an absolute must. You can also do it with critical.
Okay, one last question, because we are overflowing time. So you already had your chance.
Okay,
I'd like to give the mic there.
Let me ask a very short and easy question, if you don't mind. You will be slightly subcritical. How you will set up, how you will reach this slightly subcriticality? And in case that you will do it with control rods, can you exclude criticality accidents?
If we are below criticality, there is no criticality accident.
How you will set up your criticality? How you will set up that it will be 997, 993? How you will set up it by
there are ways of measuring it. I mean, you know, because the question is that we have a very nice experiment which we can measure it. Because when you get close to criticality, still without reaching criticality, when you get to 0.9, 0.95, etc., you get a lot of noise coming out because of the fact that you have the chain reaction is developing longer. For instance, if I take a neutron, there are neutrons going around. When a neutron comes out, it can produce secondary cascade, and then more neutrons and more neutrons and more neutrons. In the case of criticality, this thing is going to infinity because it always produces as many neutrons as you've lost. If you're below criticality, then the number of neutrons is less than what you have. But the number of neutrons you see is depending on K. So what you do, you go with the counter, and you look at the number of the time the neutron takes to dissipate away, and the number of neutrons you have present, and that it gives you directly a measure of K.
How you will control this measure? How you will reach the...
You measure it, and then you can control the control bars.
Control bars.
Sure.
And in case you will have control bars, can you not have a criticality accidents based on the mishandling of control bars?
Mishandling control bars. I don't know. Mishandling of what? I don't know what it is. Control bars are perfectly fine. I mean, if you say that your problem is mishandling of control bars, I think we are in the wrong business. Control bars is a perfectly legitimate system to reduce the radioactivity of a system. I don't know. Anybody would come along and say, control bar are a problem. I mean, somebody has to explain to me. I put the control bars in there. I eat the neutrons, the end of the story. I don't see, I mean, you should confuse real problem with pseudo problem. I mean, it seems to me that the fact that you cannot control a control bar is a pseudo problem. That's my view, but maybe not your case. We'll see.
Okay, so I propose we thank again Carlo Rubbia.